Looking at this network map, you are seeing over 700 actively compromised web domains. These nodes represent universities, financial technology firms, blockchain networks, and SaaS platforms, organizations that rely heavily on their digital reputation. The common denominator across all of these breaches is a single point of failure, CVE 2026-26980. This is a critical SQL injection vulnerability, carrying a severity score of 9.4 out of 10, located deep within the Ghost content management system. Despite the scale of these breaches, the targeted websites remain fully operational. There are no ransom notes or database wipes. The core services of these institutions continue to run without interruption. Instead, the attackers are quietly modifying site content to host clickjack attacks, a method that uses the site's legitimate domain to trick visitors into compromise. Tracing this threat means mapping exactly how an attacker translates a back-end database flaw on a web server into a remote access Trojan running natively on a visitor's operating system. This diagram shows the foundational architecture of Ghost CMS, a content API for public articles, an admin API for managing the site, and a database for sensitive records. The vulnerability exists within the content API, allowing external, unauthenticated requests to pass through without valid credentials. By crafting a specific payload, attackers use that unauthenticated route to execute an SQL injection, forcing the database to process arbitrary read commands. They use this access for one specific target, querying the database to extract the master admin API key. That key is designed to give site administrators the ability to directly modify, publish, or delete content across the entire management system. Acquiring this credential escalates the attack from a passive read vulnerability into unauthorized, programmatic write access over the entire website. Once the admin API key is secured, the attackers immediately automate the exploitation. They don't rewrite articles by hand. They deploy scripts that send bulk post and put requests to the CMS backend, cycling through hundreds of published pages in seconds. This illustrates what those requests modify. The article's content is left untouched. Instead, the focus shifts to the absolute bottom of the document object model. Here, attackers append a two-stage JavaScript loader into the HTML footer of every page. This loader is entirely lightweight. It contains no malicious executables and triggers no immediate alarms. It functions solely as a beacon, waiting for a visitor's browser to execute it. Because this beacon sits within the HTML of a university or a financial institution, it inherits the parent domain's legitimacy, easily slipping past automated reputation filters that block known malicious sites. When a user visits the compromised article, their browser reads the injected script and automatically reaches out to an external server, mapped here as clo4shara.xyz. Hosted on this server is a PHP traffic distribution script powered by a commercial cloaking service known as AdSpect. The script aggressively profiles the incoming connection, collecting unique metrics to build a detailed fingerprint of the visitor's browser. This fork illustrates the cloaking logic. AdSpect analyzes the fingerprint and divides the incoming traffic into two distinct streams. If the fingerprint matches an automated security scanner, a web crawler, or a sandbox environment, the script serves back a completely benign web page. The security tool reports no threat. But if the metrics confirm a valid human user, the script delivers an iframe element containing the active attack payload. At this stage, the PHP script supports 19 different commands, allowing the attackers to trigger arbitrary JavaScript, force redirects, or launch downloads depending on the victim's profile. Dynamic fingerprinting keeps the campaign entirely invisible to defensive web scrapers, reserving the heavy payloads exclusively for high-probability human targets. Validated targets are immediately presented with this UI, a realistic but entirely fake capture verification page nested inside the iframe. This is a ClickFix attack. It bypasses the technical sandboxing of modern web browsers by manipulating the user into executing the malware themselves. The prompt instructs the user to copy a provided text string, open the Windows Run dialog, paste the text, and hit Enter. When the user pastes that string into the Run dialog, they execute an obfuscated base64 command, revealing a nested delivery architecture. The first stage acts as a dropper, downloading a remote zip archive to the local machine. Next, a hidden Windows batch script extracts from that archive and automatically runs. Finally, the script invokes PowerShell, utilizing native OS tools to download the ultimate binary payload. By leveraging human interaction to launch these commands, attackers circumvent the browser's security boundaries, moving execution directly onto the host operating system processes. To mask the installation, the PowerShell instance hands execution control over to run-dll32.exe, a legitimate Windows process often ignored by standard monitoring. Simultaneously, the script opens a generic, distracting web page in the user's browser, holding their attention while the payload unpacks in the background. Security analysts observed two variations of the final payload. Some endpoints received a malicious DLL disguised as a PuTTY client, carrying a valid code signing certificate. Others received an Inno setup installer for a modified Electron application based on the open-source Grape client. Regardless of delivery, the application buries itself in the System Startup folder. Once installed, it establishes a quiet rhythm, pinging a remote command server at webtelegram.ug every 30 seconds for new instructions. The entire Ghost CMS exploit chain, from the initial database injection to the JavaScript cloaking, exists simply to establish this resilient, continuously polling backdoor. This pipeline illustrates the full scope of the threat. A database vulnerability leads to credential theft, which enables JavaScript injection, resulting in social engineering and ultimately endpoint compromise. The immediate technical requirement for Ghost CMS administrators is upgrading their instances to version 6.19.1 or higher to close the SQL injection vector. However, as this checklist shows, patching the software is only the first step in remediation. Applying the software update prevents future database reads, but it does nothing to invalidate an admin API key that was already stolen. Administrators must manually rotate all credentials. Every published article and page must be thoroughly inspected and scrubbed to remove the injected JavaScript loaders from the HTML footers. Security teams must also audit their access logs, looking specifically for unauthorized admin API invocation during the contamination window to determine if bulk modifications occurred. The Ghost CMS campaign demonstrates that back-end API vulnerabilities extend beyond the threat of data loss. They turn trusted digital infrastructure into a high-conversion delivery vehicle for social engineering.